Hello there, Mr. Chan here for Algebra 2. Please grab your note taker, your student companion, and turn to page 117. We are going to start 5-2, Properties of Exponents and Radicals. All right. Olivia was practicing evaluating and simplifying expressions. Her work for 3 expressions is shown. Number 1, 2, and 3. Is Olivia's work in the first example correct? Explain your thinking. So right now we have 24 squared. What she did was she broke up 24 squared to 416. Unfortunately, that is incorrect. She was trying to square 20, I guess, and 4. That doesn't come out to 416. The true square of 24 squared is 576. So you can't separate 24 before you square it. So that's the part that's illegal. That's what she tried to do. And that's illegal. Not the same. How about the second one? What's going on there? 3 to the 6th power equals 9 times 27, and that equals a 270 minus 27. Interesting. Now, I don't know where she got 9 times 27. That's where the mistake is for that one. Let's go ahead and bring that down here. Three to the 6th power, she's trying to say it's 9 times 27, but 9 is 3 squared, isn't it? If we were to like use 3's as our bases, 27 is 3 to the 3rd. The rules from back in Algebra 1, we have 3 squared times 3 to the 3rd. The rule is to add the exponents. And if we add the exponents, 2 plus 3 doesn't equal to 6, right? So that's where she made that mistake. That's where she made that mistake. Great. How about the next one? The square root of 625 is equal to the square root of 400 plus the square root of 225. And that's incorrect. Oh, by the way, 3 to the 6th power, let me tell you that particular answer is 729. Forgot to mention that from earlier from my calculator. Number 3, let's bring that down. Square root of 625, there she's claiming is the square root of 400 separated plus the square root of 225. All I can tell you is that it's illegal. In fact, I do know from experience the square root of 625 is 25. And we know that the 400 is 20 and the 225 is 15. So 20 plus 15 is not 25. That's fine. That's illegal. Okay, great. Let's go to the bottom here. I'm going to find some spacer. Some of the mistakes she was just showing on her problems stems from not knowing the properties of exponents. Okay, I'm going to throw 5 of them at you that you learned in Algebra 1. The first one, of course, is a to the m times a to the n. Here, when it comes to the product property of exponents, the rule is to add the exponents. That's the rule. The opposite of product, of course, is quotient. That's next. We have a to the m divided by a to the n. Here, the rule is to subtract the exponents. Next one is called the power of a power. A to the m to another power n. Here the rule is to multiply the exponents. Okay, we also have zero powers. A to the 0 power is 1. These are all, should be all review. Let me know if you need me to prove them to you. I'd be happy to. The next one, of course, are negative exponents. What happens if I have a negative power? A to the negative m power, let's say. Well, this equals 1 over a to the m. And again, let me know if you want me to prove that for you. We have a habits of mind at the bottom here. You know that 3 squared plus 4 squared equals 5 squared. Sounds familiar. Does the square root of 3 squared plus the square root of 4 squared equals the square root of 5 squared? The answer is no. They're trying to square root both sides, but you cannot separate the square root between a plus sign. That's illegal. Okay? What you should have done is this. The square root of the whole left side, 3 squared plus 4 squared. That's what they should have done. In fact, this is the Pythagorean theorem. A squared plus b squared equals c squared. All righty, not too bad. Let's switch to the next page. Here we go. Use properties of exponents. How can you rewrite each expression using properties of exponents? Well, when they ask you to do that, we want to keep in mind that we want to put it in reduced radical form. All right, here we go. Let's try number 1a. 3 over 32 to the 2/5 all to the 1/2 power. Holy cow. That's like a mess there. But the one thing that sticks out, and don't worry about the fractions. The one thing that sticks out is this power on the outside. Let's go and apply the power. Let me zoom in a little more so you can see it better. We're going to apply the 1/2 power to everything inside the fraction. We've got 3 to the 1/2 power over 32 to the 2/5 to the 1/2 power. Okay. Next one. Looking at this mess, I see a power over power going on here. The rule for power over power is to multiply. Let's do that next. So 2/5 times 1/2. Ooh, interesting. The 2's cancel. That gives me 32 to the 1/5 power. Ah, this is very fascinating. Now, as you know from Algebra 1, sometimes when you look at a base that's kind of big, in this case 32, maybe we can break that down a little bit. Let's do that. 32 is 2 times 16. 16, of course, is 4 and 4. And those will break down to a pair of 2's. Oh, look at that. 32 is 2 to the 5th power, and we're looking for the 1/5 right there. That's kind of interesting. Let's clean that up. So we have 3 to the 1/2 over 2 to the 5th from a second ago. Use the color here, 2 to the 5th to the 1/5 power. Aha, we have power over power right here again. Multiply those two. Oh, that cancels. That's interesting. Those cancel. That's 2 to the 1st. So we have 3 to the 1/2 over 2 to the 1st. And that's it. You guys recognize this thing, 1/2 from Algebra 1. Okay? If we convert that to a radical form, as you recall, fraction powers are a to the m over n is equal to the nth root of a to the m. This is a rational exponent. Also known as a fraction power. Right? This is back for an algebra 1. I'm going to take that 3 to the 1/2. That's literally the square root. So I can make this look nicer with radicals. This is the square root of 3 over 2 as my answer. Okay? Not too bad. Any questions? Let me know. All right, let's try the second one. Here we go. Wow, a lot going on here. Take your time. We have 2a to the 1/3. Notice the 1/3 is only attached to the a, not to the 2. Be careful there. And we have times ab to the 1/2 to the 2/3. The one thing that sticks out first to me is that power on the outside. That's going to apply to the pair of parentheses. Let's apply the power and see what happens, okay? 2a to the 1/3 doesn't get touched at all. However, inside the parentheses, we have two items, a to the 2/3 and times b to the 1/2 to the 2/3. See, I'm just applying the power, no big deal. Let's clean, oh, look at this. This is interesting. Those a's are multiplying. The rule for product of powers is to add the exponents, right? So this is going to be 2a to the 1/3 plus 2/3. And over here on the back end, we have a power of a power. And the rule here is to multiply those powers. Notice the 2's go away right there. Isn't that cool? So this is b to the 1/3. Okay. Let's keep going. Oh, look at that. 1/3 plus 2/3 is 3/3. Nice. And then 3/3 is just 1. 2ab to the 1/3. Now they want this to be written in radical form, okay? That's what they want us to do. So this part right here, this is the cube root. Something from Algebra 1 you should have picked up. If you didn't, that's okay. And there's your answer right there. All right, very nice. Let's try number 2. Any questions on number 1b and 1a? Nice. All right. Ooh, we're now going to use properties of exponents to rewrite radicals. How can you rewrite each expression? Well, we're just basically looking at the index or the root. In this case, for number 2 is the 4th root. We're looking for 4 factors to come out of there. Let's break down the 81. That's easy. 9 times 9, 3 times 3. Okay. A to the 8th, you can look at it as AAA, and then B's are B to the 5th. You can look at it that way. I'm going to actually expand them out underneath the radical to just physically show you. So far we have 3, 3, 3, 3, and a bunch of A's. Holy cow, A, and a bunch of B's. Because I saw the 4 there, I'm already like grouping them into groups of 4 here. Oh, we have a group of 3's, yay! 4 3's comes out as a single 3 right there. Ooh, 2 quadruple pairs comes out as a single pair of A's right there. How about B's? Look at the B's here. There's a group of b's right there. Oh, which means we have this extra leftover b on the inside. So what do we do with that? That's the question. Stays in there. So my final answer is 3a squared b times the fourth root of b. That's how you say that. Okay, not too bad. Not too bad at all. Woo! A lot of manual work, and that's what is required sometimes. Sometimes you don't just see it right away. All right, we're looking for the cube root. Letter 2b here. This is the cube root, or the third root. Great. Expand manually. I see the 125. That's breakdownable. That's 525. That's 5 and 5. Nice. Let's expand this. X, 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 Y, Y. Oh, I see. 5, 5, 5, X. Notice a couple of the X's go away. Bam. But I do have a grouping here. A group of 3's come out on top there. The Y's are stuck there, but the group of 5's on the bottom. That works, right? Okay, those come out. Nice. X over 5. But then we have this couple of pair Y's that are stuck underneath the radical. Like this. And there's your answer. Okay? I mean, you can put the radical in the numerator only. That would be fine too. So this will work too. Okay? They're both acceptable. All right. We're going to skip the habits of mind just underneath it. Let's jump to example 3. All right, let's do that. Ooh, rewrite the product or quotient of a radical. What is the reduced radical form of each expression? Okay, so here's the thing with radicals and fractions. You cannot have a radical in the denominator for quotients, okay? So let me write that down right here. If you have stuff in the numerator, fine. But in the denominator, if you have a radical, that is not allowed. That's in the denominator. Radicals are not allowed in the denominator. When that happens, you have to do something called rationalize the denominator. That is the key. You need to rationalize the denominator. Basically, we're manipulating the fraction into another form of itself that's not reduced, so to speak. We're unreducing it. We're changing it so you don't have a radical in the denominator. I'll show you in a moment how that looks, okay? All right. So let's take a look at number 3a here. We're looking for the fifth root. We need 5 to come out. 5 factors. Now, right away, we have an issue. 16 breaks out into 4 2's. That's not 5. It's in the denominator too. So that's going to be a problem, isn't it? So far we have that 7 on top. And on the bottom we have 2, 2, 2, 2, x, x, x. We don't like radicals in the denominator. So there's a way to patch this radical but not change the original problem in the first place. We're going to multiply by 1. To rationalize the denominator. Now, 1 isn't just 1. We're going to do it by some form of 1. Look at the bottom again, the denominator. I have 4 2's right now. 2, 2, 2, 2. I need one more 2 so I can fifth root it to come out of the radical. So watch this. I'm going to multiply top and bottom by a 2. Because isn't that technically 1? Okay. I'm not changing the problem, right? Anytime you multiply by 1, the number is still a number. Look at the x's. How many x's do I have right now? I only have 3 of them. I need 2 more. Let's introduce 2 more arbitrarily, but in the denominator and the numerator. That is another form of 1. Right? You guys agree? This is nothing. That's just 1 right there. And that is the key. Multiply everything by the fifth root of that stuff right there, okay? And we're extending this. And we're extending that, okay? So right now, we now have in the numerator the fifth root of 7 times 2 times x times x. You all see that? 7 times 2 times x times x. That is 14x squared. In the denominator, all the 2's come out, yay, as a single 2. All the x's come out as a single x. And that's how you rationalize the denominator. That, ladies and gentlemen, is the same as the original. Those mean the same thing. Weird, huh? And one of the main reasons why we rationalize the denominator, because when you're doing algebra, it's just easier not to deal with radicals in the denominator, that's all. Letter B is a little easier, it's quotient. So letter A was, is a product. Letter B is a product, and letter A was a quotient. They gave us the quotient first, and we're doing the product second here. All right, so we have a fourth root and a square root. We cannot combine those together, unfortunately. We're going to have to play around with it, just manipulate it. So right now I'm looking at this particular problem, and there's a trick to this problem. It's kind of crazy, to be honest with you. Let's convert the radical, the fourth root of 27x squared, into a fraction power. Let's do that right now, okay? So this is 27x squared to the fourth power, okay? That's kind of weird. We're going to convert the other one as well. 3x to the 1/2 power. Now, where the heck is 1/2? Well, the 2 is right there. And if you don't have any powers thrown at you, just assume it's 1. So that's the square root is 1/2. Okay? All right. What I'm going to do right now is I'm going to do something very, very strange. Oh, by the way, I don't know where I got that 4 from earlier. That's 1/4, I meant to say. Sorry about that from the first fraction. That's 1/4 power. Whoops. Okay. So what I'm going to do is I'm going to somehow apply a power backwards. We have a 1/4 and a 1/2. Can I rewrite the 1/2 into a different form of itself? Watch this. This is pretty crazy. I'm going to change 1/2 to 2/4. This is a trick problem. Kind of interesting they're giving it to us, though. Woo! That's pretty crazy. There, I'm undoing power of a power. It's like unreducing, right? Okay. And then I'm going to do something else to that. I'm going to undo power applying, okay? Let's do that too. Watch this. This is kind of strange. I'm going to break up the 2 and the 4 like this. Isn't that crazy? Woo! Did I say power of a power? Okay. We're going to do that twice. So I'm just breaking up the 2/4 into 2 times 1/4. Isn't that crazy? You see where I have the 1/4 now? Bring this guy down. from in front earlier, now they both have 1/4 powers. Isn't that strange? Okay. I'm now going to do this backwards. I'm going to undo powers backwards this way. It's kind of crazy. I know. So watch this. 27x squared and 3x squared, like that. There's a lot of parentheses here. Watch out, everybody. To the 1/4 power. Woo! Wow, a lot of parentheses there. Then I'm going to concentrate on inside the parentheses. We have 27 and 3x squared. Let's clean that up. 3x squared is 9x squared. That's crazy. Woo! 27 times 9 is 243. X squared times x squared is x to the 4th. Isn't that crazy? Woo. Wait a second. I'm now going to go forwards with applying the 1/4 power to everything? That's pretty nuts, Mr. Chad. I know. Really crazy. So let's do that one too. I'm running out of room here. So I'm going to do 243 to the 1/4 power and the x to the 4th to the 1/4 power. Wow. You see why I did that? Because those will cancel each other out when you do power over power. That 4 and 1/4 becomes x to the 1st. Where's that going in circles, aren't we, Mr. Chan? This is crazy. And 243 to the 1/4 power, is that break-it-downable? I don't know. What do you guys think? Let's break down 243. Yeah? Now, remember from earlier where we got 243? It was 27 times 9. 27 is 3 times 9. 9 is 3 times 3. And that other 9 is 3 times 3. I didn't have to multiply the 27 and the 9. I have 5 3s. And that 1/4 power means I need 4 of them to come out of the radical. So let's bring out a group of 4s there. That comes out as a single 3. Ah, we have a stuck. We have an extra 3 underneath the 4th root. And there's your answer, ladies and gentlemen. After all that work, that's a crazy problem there. 3x times the 4th root of 3 is your answer. Okay? Woo! Next page. Thanks for hanging in there. All this stuff gets a little more complicated at the Algebra 2 level. Wow. Example 4, we're asked to add and subtract radical expressions. Anytime you try to add and subtract things, they have to be like radicals. That's what we need to find. Right? Think of Halloween candy. After you finish trick-or-treating, you need to sort all your different candies up. You can't just combine M&Ms and Snickers together. There's no way to sort them and count them. So when it comes to adding, subtracting, you want to make sure you have like radicals, okay? Right now, clearly 4a and 4b do not have like radicals. In fact, I am going to go ahead and do b first. It's a lot easier, I think. Break down each of those radicands. The numbers underneath the radical. 20 breaks down into 4 and 5. Circle the prime factors. Bam, there's that first one. So when we're trying to simplify the square root of 20, we have 2, 2, 5. Pair of 2's comes out. So the square root of 20 is 2 root 5, right? Makes sense? Okay. Minus 600, let's break that down. 6 and 100. Oh, 100's easy. 6 doesn't work that well, but 100 is 10 and 10. Here's my pair right there. It comes out as a single 10, but 2 times 3 stuck underneath the radical goes back to 6. Then finally, the back half, 125 is break it down by 5. Aha. So 125 is 555. Pair of 5s do come out. There's a single 5. But we have a radical 5 underneath that's stuck. Now look at these 3 radicals here. We have 2 of those root 5s, minus 10 of those root 6s, minus 5 of those root 5s. The root 5s can only be combined together. The middle term has no other radical to combine with. So you just treat it like a variable, like 2x minus 5x. 2 root 5 minus 5 root 5 is negative 3 root 5. And bring down the other one that had nothing to do. Okay, there it is. That's your simplified radical after adding, subtracting. 4a is a little crazier looking. The first and the last term have cube roots on there. We need to find 3 of something. Let's break down the 2000. Of course, 1000 is 10, 10, 10. Notice I'm going to stop there because there's my triple. In fact, ladies and gentlemen, the cube root of 2000 is that triple 10 comes out as a single 10 times 3 root the leftover 2 underneath the radical there. I have a feeling that 2 is just stuck. Let's break down the 128, see what happens there, okay? 128 is 2 times 64. 64 is 8 times 8. 8, of course, is 2 times 2 times 2. Oh, look at those triple 2s. Here's a triple 2. And here's another triple 2. So those come out. Minus 2 times 2 times. Oh, there's a leftover 2 over there. The cube root of 2 like that. Which means my expression is now 10 times cube root of 2 plus the square root of 2 minus 4 times the cube root of 2. Notice the cube root of 2s are like terms, so those can be combined together. Yeah, like radicals. 10 of those minus 4 of those is 6 of those funny looking radicals. 6 times the cube root of 2 plus the square root of 2. Okay, and that's it. All right, we're going to skip this habits of mind right here. Let's jump down to example 5. Oh, after adding, subtracting, we're going to multiply radicals. Okay, fine. That seems to be a little easier. I see that in the first one we have a FOIL with a product of 2 binomials. So we do have a FOIL situation. Here we go. First terms, x times x. Sweet. You can throw it in a box if you like to, no big deal. In fact, some kids do like that. Outer terms, x times root 10 is plus x root 10. Okay. Inner terms, we have minus x root 10. Oh, those go away. In fact, oh yeah, don't you recognize this is a product of conjugates? Interesting. And the last term, we'll be careful here. This is a little tricky. Negative times a positive is a negative. Root 10 times root 10 is regular 10. Like that, okay? That's the square root of 100. Oh, wait, yeah. Square root of 100, that should not be a radical right there. Sorry about that. It's square root of 100. Hey, those inner and outer terms go away. And my answer is x squared minus 10. Yay. Ooh, the next one is not FOIL, but distributive property. Let's do that. Oh, be careful here, okay? The 6 is underneath the radical, the 5 is not. Those are separate. So root 6 times 5 is not root 30. That would be bad. It's It's 5 times root 6 like that. They're separate. They can't be combined together. However, the back half, kind of interesting, root 6, the square root of 6 times the square root of 3, we can put those radicand numbers together plus root 18. But be careful. Didn't root 18 just come from 6 times 3, right? In fact, maybe we shouldn't have done that in the first place. Let's go ahead and re-separate them. As 6 times 3. The 6 is 3 times 2. Aha! So that can be simplified. The square root of 18 from earlier, moments ago, is the pair of 3's come out, but the 2 does not. And there's your answer right there, okay? All right. If you have any questions, let me know. Whew. So we've got addition, subtraction, multiplying. Now we're going to do dividing. Uh-oh. Our denominator is a binomial. Okay? It's a little different from earlier when we did example 3, I believe. Let me take a quick peek here. Oh, yep. Example 3a involved individual monomial radicals. Here, we're dealing with a radical in the denominator that's a binomial. When that happens, how do we rationalize it? We multiply by the conjugate. The conjugate of a plus root b is a minus root b, okay? Those are conjugates. That's what we need to multiply by. That is the strategy. Look at number 6a. We have a binomial over another binomial, and these happen to be very ugly radicals that are binomials. Parenthesize as soon as possible, please. The only thing that matters is to get rid of that radical in the denominator, in this case 2 minus root 3. The conjugate of 2 minus root 3 is 2 plus root 3. Let's do that. If I do it to the bottom, I got to do it to the top, meaning the numerator as well. Because we are multiplying by a form of 1, aren't we? That's a form of 1. Woo! Ready to FOIL? I like to do the denominators first. It's just easier for me. Let's do that. All right, here we go. First terms, 2 times 2 is 4. Nice. Ooh, when you multiply conjugates, the O and the I do go away, but I'm going to just show you. 2 times root 3 is plus 2 root 3. Then the outer terms is, the inner term, sorry, because we're doing foiling, is root 3 times 2 is minus 2 root 3. And then last terms is root negative times a positive is a negative. Root 3 times root 3 is root 9, or simply 3. Please be careful there. The inner and the outers go away. Oh, look. 4 minus 3 is 1. That's it. Pretty easy, huh? Okay. Oops. 1. The numerator, I do need to traditionally FOIL that one. Let's do that one now. Here we go. 5 times 2 is 10. 5 times root 3, be careful, they're separate, is plus 5 root 3. Inner terms, be careful there. Negative root 2 times 2 is minus 2 root 2. And last terms is, oh, they're both underneath the radical. It's going to be negative root 2 times 3 is 6. Now, this is kind of crazy. I'm looking at these 4 answers here. Nothing combines together. That's your answer. Isn't that strange? All right, let's take a look at B. We do have a conjugate, a binomial that happens to have a radical. We need to multiply by the conjugate of 1 minus root x, and that is 1 plus root x, top and bottom. Here we go. I like to do the denominator first. Let's do that. Oh, by the way, I just noticed something. No, it's fine. Okay. Let's FOIL the denominator. We have 1 times 1 is 1. Outer and inner terms do cancel. And last terms, be careful here. Negative times the positive is a negative. Root x times root x is regular x. Those go away. Let's do the numerator. Looks like the distributive property. Here we go. Negative 4x times 1 is negative 4x. And negative 4x times root x is minus 4x root x. All right. This is a little crazy here. We now have negative 4x minus 4x root x over 1 minus x. Now you might think that we're done. In fact, we are done. But you can always check, though. You guys want to check. You never know whether or not we can factor out something to reduce or not. But that is the answer. I'm kind of staring at it right now. Make it 1 minus x. Maybe take out a negative. No, it's very close, though. It's very close, to be honest with you. Hey, we have a question at the bottom here. Is the product of two irrational binomials always rational? Let's see. Irrational binomials. Yeah, we're going to skip that. Let's move to the next page. Last page. Woohoo! There we go. Woo. All right. Number 5. What is the reduced radical form of each expression? We have 49 to the 3/4 times 49 to the negative 1/4. I don't care about the fractions and the powers of them. The key is, what's the rule for the product of exponents? The rule is to add the exponents because the base is the same, okay? Let's add them. 49 to the 3/4 plus, now this is the weird part, negative 1/4. 3/4 minus 1 is 2/4. 2/4 reduces to 1/2. Oh, isn't that the square root of 49 when you rewrite it as a rational exponent? Sorry. What's the square root of 49, class? 7. Yay. Done with number 5. Number 6. I'm going to apply the power here. 3/4 is just screaming it at me to apply to everything inside. So we have, of course, 3/4 applied to the a squared, the b to the 8th, and a to the 1/3. Let's do that. A squared to the 3/4 power. The b to the 8th gets brought to that as well. All over a to the 1/3 to the 3/4 power as well. Okay, let's clean that up. A squared to the 3/4 multiply, 6/4. Oh, b's power. B times 3/4 is 24/4. You can see where they can be reduced soon. A to the 1/3 times 3/4 is 3/12. Let's go ahead and clean that up. Reduce them. Interesting. That's 3/2. B to the 6. We're going to reduce the 24 over 4. Very interesting, right? Just reduce. Oh, this is reducible too. Interesting. And this is a to the 1/4. You guys remember the rule for division of exponents? The rule is to subtract those powers right there. Let's do that. A to the 3/2 minus 1/4 in the denominator times b to the 6. Ooh, 3/2. I got to convert that back to 6/4. Embarrassing. 6/4 minus 1/4 is 5/4. And I guess they want us to reconvert that to a radical. Wow, crazy. This is the 4th root of a to the 5th times b to the 6th. Look at that. Break that down. A. Bring out a bunch of those as a single. Oh, that comes out A. Great. There is a leftover A right there. And times b to the 6 times the 4th root of A. Wow, look at that funny looking answer. Okay, not too bad. Ready for number 7? Woo. Any questions, let me know. Number 7 is the 4th root. We're looking for 4 factors. Ooh, breaking down 1024. Did you know that 1024 is 32 times 32? I mean, you can start breaking it with 2's, but I'm just going to tell you, I kind of know that one. 32 is a bunch of 2's, 5 of them for each pair of those. A lot of 2's there. Ooh, x's, let's break those down. Notice I grouped them into 4's and y's. All right, let's clean it up. Looking for quadruples. There's 1, there's 10. Oh, yeah. So it's 2 x's, x. No more x's. We do have a couple of leftover 2's though. And a single x area. 4 y's, y, times the 4th root of the leftover things. We have a 2 and a 2 and an x. Clean that up. 4x squared y to the 3rd times the 4th root of 4x. Wow, that's crazy. And we do need to be careful with even powers. I forgot to mention this earlier. We don't know if those variables that come out of the radical are positive or not. We have to force it to be positive. To do that in algebra, we throw around, look at these, I mean, look at the x here. If x was negative, it doesn't matter because when you square it becomes positive. However, with the second one, if y is negative, we can't fourth root negative numbers. So we have to force it to be positive like that. And ladies and gentlemen, there it is, my absolute value symbol right there to make it positive, which gives me an answer because I had to do that because of the 4th root. All right? Okay. Crazy. Number 8. Looks like I'm going to have to clean up any radicals in the denominator. I'm looking for 3. That is the index, isn't it? Unfortunately, I don't have enough numbers to come out of the radical. I know that 4 is 2 times 2. I know that 9 is 3 times 3, and m squared is m times m. Do I have enough to rationalize the denominator? No, I need to introduce an additional 3 tops and bottoms and an additional m top and bottom like that, okay? So I'm extending it. This is a form of 1. Yay, you look at the denominator. Let's clean that up. This is now the cube root of, in the numerator, 2 times 2 times 3 is 12m. Denominator, I have a triple 3 and a triple m. And there's my answer, yay. And by the way, you cannot reduce across radicals. Don't be tempted to cancel those m's. One's on the inside, one's on the outside. And so is the thought for 12 and 3. They cannot be reduced that way either. Number 9. A lot of operations with radicals, isn't it? A lot of things going on here. All right, we have 3 radicals that are not like radicals. We need to break them down and simplify each one. 63 is 9 times 7. Break down the 9. Oh, that's 3 root 7. Yay. So the pair of 3's come out, yeah. 700, let's break that down. Ooh, we do know the square root of 100 is 10. So that's nice. I'm going to break that out. So that's going to be minus 10 root 7, yeah? And the last one, 12, let's break that down. I don't really know some numbers that break into 112, so I'll do it manually, okay? That is 2 times, what is that? 56. Aha, 56 is familiar. 7 times 8, that's 222. Interesting. I have a pair of 2's over here and another pair of 2's over here. But I do have a leftover 7, so that's going to be minus 7 times one of the pair of 2. Wait a second. Sorry, I didn't mean to say 7. The 7's underneath the radical. First pair of 2's comes out, and the second pair of 2's comes out, but there's a leftover 7 underneath. That's what I meant to say. Sorry about that. So that's minus 4 root 7. Oh, everything's a 7. Yay. So all 3 of these radicals are all like radicals. You just look at the coefficient. 3 minus 10 minus 4 is negative, what is that, 11? Negative 11 root 7? Okay. It's like a variable, right? It's like saying 3x minus 10x minus 4x. That's all it is. Ooh, almost done. Number 10, looks like we need to multiply root 5 to that binomial there. Root 5 times 6, of course, they are not numbers that can be multiplied together. That is simply 6 root 5. Then plus root 5 times root 2 is root 10. And that's it. That was pretty short and fast. Yeah. Ah, number 11. I have a radical in the denominator. I need to rationalize the denominator there. My nose is getting stuffed up. Allergies. Sorry about that. Root 6 is a single monomial. All I need to do is multiply by the same radical, tops and bottoms. Okay? This is a form of 1 now. Root 6 times root 6 in the denominator is regular 6. On top, we have 3 root 6. And that can be reduced this way. 3 goes into 3 once, 3 goes into 6 twice. And there's my answer right there for number 11. Root 6 over 2. Yay. Ooh, I'm ready for the last one. We're approaching an hour. How did this get out of hand? The last one is a binomial in the denominator. I need to rationalize the denominator by multiplying by the conjugate. Let's do it. We need the conjugate. All right, the conjugate of root 5 plus 3 is root 5 minus root 3. Okay. I'm sorry, minus 3. Okay, multiply the numerator and the denominator. Let's do it. I like to do the denominator first. When you FOIL, the O and the I do go away. You don't have to even worry about those, okay? Root 5 times root 5 is regular 5. And the back half, 3 times negative 3, is negative 9. I don't even bother with the O and the I because I know they disappear. I know that. 5 minus 9 is negative 4 in the denominator. In the numerator, let's apply the distributive property. Root 7 times root 5 is root 35. They're underneath the radical. And root 7 times negative 3 is minus 3 root 7. And that's it. Can't do anything else with that thing. It's an ugly answer, I know. I think we pulled it off. Is it an hour? Not even an hour. Great. Thank you very much. Have a nice day. Until next time, bye-bye.